So to differentiate, f of x is equal to 3x plus 1 divided by x squared plus 1. We'll need to use the quotient rule. So f dashed x is equal to, we differentiate the top of the fraction, so that's 3, multiplied by the bottom, x squared plus 1 in brackets. Subtract from this the top left as it is, the 3x plus 1 in brackets, multiplied by the bottom differentiated, which is 2x. So that's minus 3x plus 1 in brackets times 2x. This is then all divided by what's in the bottom squared. X squared plus 1 all squared. You can simplify this by multiplying out the brackets on the top. So that will be 3x squared plus 3, and then minus 3x times 2x is minus 6x squared, and minus 1 times 2x minus 2x, all divided by x squared plus 1 all squared. 3x squared minus the 6x squared is minus 3x squared minus 2x plus 3 over the bottom all squared, which is x squared plus 1 all squared. For part B, g of x is equal to cos squared x times x of tan x. X of tan x is more normally written e to the power tan x, so we'll write it like that. So g of x is equal to cos squared x times e to the tan x. We have to differentiate and find g dashed x. We'll use the product rule here. The product rule tells us to differentiate the first function, cos squared x. Differentiating cos squared x, that's cos x all squared in brackets, will be 2 times cos x times the cos x differentiated, which is negative sin x. So that will be negative 2 cos x times sin x times the e to the tan x left as it is. We add on to this cos squared x left as it is, multiplied by e to the tan x differentiated. Now e to the tan x differentiated gives e to the tan x times the tan x differentiated is sec squared x. So this is multiplied by e to the tan x times sec squared x. Minus 2 cos x sin x. Now there's a formula, 2 sin x cos x is sin 2x, so we could replace this by minus sin 2x times e to the tan x. Sec squared x is 1 over cos squared x, so we'll replace that by 1 over cos squared x. That then enables us to cancel off in the second term the cos squared x's. So we've got minus sin 2x e to the tan x plus e to the tan x. We can reverse the order here and then take out a common factor of e to the tan x, and inside the brackets will be 1 minus sin 2x. So we're told that the first term for geometric series is 2048, and the fourth term is 256. We're asked to calculate the value of the common ratio. Now the terms of a geometric series are a, ar, ar squared, ar cubed, and so on. So a is equal to the first term, a is equal to 2048. The fourth term will be ar cubed. So ar cubed is equal to 256. We can find r from this if we divide ar cubed divided by a. That will give us r cubed. We then divide 256 by 2048, which is exactly 1/8. R cubed is equal to 1/8. A half cubed is 1/8. So r is equal to a half. The common ratio is a half. We're told that the sum to n terms is 4088. The formula for the sum to n terms of a geometric series is Sn is equal to a bracket 1 minus r to the n divided by 1 minus r. The value of a is 2048. So that's 2048 minus r to the n, 1/2 to the power of n, which we can write as 1 over 2 to the power of n. And on the bottom, 1 minus r, 1 minus a half, which is a half. The 2048 divided by a half means that we end up doubling the 2048, which is 4096. And then in the brackets we'll have 1 minus 1 over 2 to the power of n. Now we're told the answer to this is 4088. So this is equal to 4088. If we now take the 4096 over and divide, we'll get that 1 minus 1 over 2 to the n will be 4088 over 4096. Rearranging this, we can get that 1 over 2 to the n will be 1 minus 4088 over 4096. We can do this calculation on our calculator, and that gives us that 1 over 2 to the n is the fraction 1 over 512. So both things in the bottom are the same, so 2 to the power of n is 512, and we can quickly do that on a calculator, realising that n would have to be 9. We're told that minus 1 plus 2i is a root of this equation. So we can do synthetic division by minus 1 plus 2i. Our coefficients of the equation are 1, 5, 11 and 15. We're going to do synthetic division by minus 1 plus 2i. First of all, we bring down the 1. We then multiply minus 1 plus 2i times 1 and put it underneath the 5. So that just gives us minus 1 plus 2i. The 5 plus the minus 1 plus 2i, the real bits will combine, and that will be 5 minus 1 is 4 plus 2i. Minus 1 plus 2i times 4 plus 2i, if we do that calculation, we end up with minus 8 plus 6i. Again, the 11 minus the 8 is 3, so this is 3 plus 6i. Now multiplying the minus 1 plus 2i times the 3 plus 6i, when we do that calculation, that gives us minus 15. 15 minus 15 gives us 0, and this happens because minus 1 plus 2i was a root. Now because minus 1 plus 2i is a root, then the conjugate of that will also be a root. Minus 1 minus 2i. So we can now do a synthetic division by minus 1 minus 2i into this part here. We've already taken out the first root. So doing synthetic division, we bring down the 1 first of all. Multiplying minus 1 minus 2i times 1 is minus 1 minus 2i, which we place underneath the 4 plus 2i. Adding them together just leaves us with 3. We then do minus 1 minus 2i times 3, which is minus 3 minus 6i. Adding these gives us 0, because it's a root. So we've now got two of the roots, minus 1 plus 2i and minus 1 minus 2i. The last root comes from here. This is a quotient. We started off with a polynomial in z cubed. This is a polynomial in z squared, so this is now a polynomial but just in z. So this 1 and 3 tells us that it's z plus 3 is our final factor. So z plus 3 must equal 0, so that z is equal to negative 3, and our three roots are minus 1 plus 2i, minus 1 minus 2i, and minus 3. The second bit was to plot all of these roots on an Argand diagram. So we draw a set of axes. The first root minus 1 plus 2i is plotted at the point negative 1, 2. Negative 1 minus 2i is plotted at negative 1, negative 2. And the last root, the minus 3, is just plotted at the point negative 3, 0.